Hello again, my dear students, and welcome to a new chapter and a new topic with our selected topic course for senior students in electronics and communication program. So, if you remember in the previous two topics, we have demonstrated two interesting phenomena related to electronics. The first, if you remember, when we deal with the tuned amplifier, I think 2 chapters ago, we have discussed together the impact of what we can call the parasitic capacitance of a MOSFET on the operation from an analog point of view when you are going to discuss or when you are going to study an analog tuned amplifier. And in the last lecture, in the previous lecture, we have also demonstrated the impact, what we can call the layout or the fabrication process for CMOS technology in general. And we have discussed together the fabrication process for a simple PN junction and also for a CMOS transistor, a complementary N-type and P-type CMOS. What we are going to do now as a final stage in this course is we are going to explore the same concepts, but from a digital perspective. I mean, the layouting, the CMOS technology from a digital perspective, as well as the capacitance from a digital perspective. And as a very simple, concrete, and essential example, we are going to consider our example on the inverter as the simplest building unit in digital environment. So, as I just mentioned, digital environments are usually considered in what we can call a logic gates. And as we know, these logic gates consist principally from series and parallel connected transistors. So the main building block for our CMOS technology, as we demonstrated earlier in this course and even in previous courses, is that NMOS transistor and the PMOS transistor. I think you already know and you're already familiar with this symbols for the NMOS and the PMOS technology. So these are the main building blocks for this technology. Okay, so this technology is seen in terms of CMOS technology, either in the N-channel MOSFET, as you can see in this case, where we have two N-doped region in a B substrate, or in a P-channel MOSFET, where we have a 2B-doped region in an N substrate, or what we can call the source and drain doping wells. So this small MOSFETs can start to be connected together to construct what we can call a transistor level circuits that can be then converted into a gate and then into a module and finally into a system, which is simply how we see the overall digital process. So what we are going today to discuss is simply this correlation between the subtransistor level and the transistor level, the coupling between these two stages, the coupling between what you are fabricating on a wafer and what you see on a transistor schematic. So this is the CMOS technology, as you can see. We have here a P-type substrate. We have this N-well so that we can construct the B MOSFET. And then we have the metal gate here for the sources, the metal gate, sorry, for the P-type and N-type. We have also a similar transistor, but in a complementary way, in an N-side way. And maybe this, I think, I'm not sure if all of you have studied digital courses or not, but one of the added points here is what we call the substrate and the well taps. These added two regions, this substrate tap and this well tap. These substrate tap and well tap are very famous in the digital technology, and they are implemented for the purpose of eliminating what we can call latch-up. The latch-up is the process of having a direct connection between the VDD and the ground in a transistor. So basically, we can say it from a point of view that in the front surface of a wafer, we are insulating connections using this insulator barriers, as you can see. So we already discussed this maybe in the previous lecture when we discussed the layouting and the VLSI technology. But what about this beyond or below the surface in the substrate? So basically, as you can see, semiconductors are everywhere under the wafer or inside the wafer. So for a high flow of a VDD connection like here, and whenever you consider this as a substrate is a ground, so there is a probability to have a connection or a direct connection between ground and VDD. You can see it very simple when you consider that you are applying here VDD, and then in the next portion of the wafer we have another ground here. So there might be a flow of current or a short circuit connection in a circuit way between this VDD and the adjacent ground and vice versa. And in order to make some sort of an isolation between this VDD terminal and the neighbor ground terminal, or what we call in digital electronics as latch-up, we start to have this high dope N region and this high dope P region. So they act as a barrier between this VDD and the adjacent or the neighbor ground, and eliminating or reducing the latch-up problem. That's why we have these taps, what we call the substrate tap and the well tap. Okay, so this is a final layout, but let's see how we are going to do some sort of a VLSI technology techniques in order to reach this final layout. As you can see, we need a lot of oxidation process, a lot of masks, lithography. We already discussed lithography one lecture ago and all this stuff. So generally, we start the story with a silicon wafer. Most likely, it's a p-doped silicon wafer. And as we discussed in the previous section, or in the previous lecture, we already started the first step by what we call the oxidation. We already have discussed the dry and the wet oxidation technique. So we start this by oxidation. And in order to make this photolithography, you need what's called a photoresist. And a first photolithography process is actually to have the well that is going to host the p-type MOSFET. So then we are using here a mask to make this well, and then we use some sort of a doping techniques we already discussed in implementation to make this N1. So this is the first step. Now we can remove the oxide and start to put another oxide, which is the gate oxide. And I think we already discussed a lot of talks before about the importance or the impact of this gate oxide in what we can call the CMOS or the oxide parasitic capacitance in a MOSFET. So after that, we can start having the position for the two gates. The one on the right is the gate for the P channel MOSFET, while the one on the left is the gate for the N channel MOSFET. Then we go to insert another passivation or oxidation layer. And then we start the doping process with our two kinds of doping. So for the N-type doping, we have three regions for N-type doping. We have the source, the drain for the N-channel MOSFET, and don't forget the N-well tap or the well tap here. So this will be the process. Then we have this three small N-doping regions, source, the drain, and the well tap. On the other hand, a similar process implemented for the p-type doping, as you can see here. Again, we have a source and drain for the p-channel MOSFET, and we have also a substrate tap here on the left, as you can see. So this is the next step. And finally, we start with adding the metals or sorry, adding the oxide first, and then adding the metal contact to make contacts for the source, the drain, the gate for these three terminals, and of course the substrate. This substrate point of view is reflected into the design in what we can call the layout. The layout is the final stage in any design process before going into fabrication or before going into fabs. So, for example, this is a very famous schematic for an inverter. I believe that all of you have already discussed digitally inverters from circuit perspective. So you know this inverter schematic. We are already going to discuss this in more details a few slides later on. So here we have an P-channel MOSFET and an N-channel MOSFET, as you can see, and this is the connection for the input. Here is the ground, and above we have a VDD, and this and that on the extreme right we have the output terminal. So this is a layout for a MOSFET. Sometimes we can make it in what's called a stack or stack diagram. It's relatively an abstraction for the layout, so it's a relatively it's more easy to be observed. So here, for example, we use this red for the P type and this green for the N type. So you know that this is the P MOSFET and this is the N MOSFET. And here we have this input connection. This is the upper terminal is VCD, and this is a ground, and this is the output. So this is a stack diagram for an inverter. And finally, I think most of you already know this normal transistor level schematic for the inverter, as you can see. And the final stage is the gate level, where you can, instead of expressing this transistor or this inverter in terms of a PMOS and an NMOS transistor, you can see it as a single gate terminal with one input, one output. But actually, our concern today is this is an introduction for our topic today, which is how we consider the capacitance in such a digital inverter or digital gate inverter. So in this case, I would recommend to go to our whiteboard. Yes, and we can stop for a while sharing the presentation. And yes, let's go deeper. Okay. So generally speaking, we already have discussed together that a three-terminal transistor, where this is the gate, this is the drain, and this is the source, can have three different types of capacitance, what we call the CGS, the CDS, and the CGD. And if you remember, we have spent a lot of time considering the CGD in the analog design. Sometimes when it's, I'm sorry. Sometimes we consider this transistor as a four-terminal device with a body terminal. So sometimes you find it in this way. So this is a body terminal. So here we have CGD, and here we have CDP, where B stands for body, and here we have CDS, and here we have CGS. So this is another consideration for a MOSFET. Okay, so this is another more detailed capacitive model for a transistor. But when we consider a digital inverter as a transistor level schematic, we have something like that. So this is VDD, and this is ground, and here is the out. So this is basically the schematic for a transistor, or sorry, for the inverter. So in this case, we can start. Of course, you know that this knob is for the B MOSFET, and this is for the N MOSFET. So in the first estimation, you can put the capacitance correlated to each of these transistors. So for example, here, for this N MOSFET transistor, we have capacitance like that. So this is CDP N, and this is CBS N, and this is CGS N, and this is CGDN, and so on. And similarly, you can have another 4 capacitors. Maybe if you open the slides, you will find the whole picture drawn as a schematic for that. Basically, these capacitors are differ from the buzzing consideration. For example, usually in an inverter, we have this body terminal here connected to the ground. So simply this CBS, or the base source capacitance, has no effect because simply the 2 terminals of the capacitance are connected to ground. So it doesn't affect the circuit. Similarly, will happen here when you have this capacitor, for example. So again, this terminal is connected to VDD. So again, this capacitance will not be of an interest because the 2 terminals are connected to VDD. But other capacitance are important as well. And we already have started discussing, maybe lectures ago, the concept of equalizing this capacitance into an input and output capacitance. So this is the way where you're going to map this inverter. So again, this is your inverter. So instead of having this interconnected capacitance, we are going to analyze the capacitance in a simple way so that we can have, by the end of the day, 1 capacitance here to the gate and 1 capacitance here to the drain. As I just mentioned, the capacitance to the source and to the body are not of interest because both are grounded. And similarly, we can have another capacitance here. So this is for the other drain, for the drain of the PMOS. And we have another capacitance here, which reflects the capacitance to the P gate, to the P channel gate. And again, the body and the source here are not of interest because they are connected to VDD. So generally, we can summarize all these 8 capacitance into 4 capacitors. 1 connected to the gate of the N-channel MOSFET, 1 connected to the gate of the P-channel MOSFET, 1 connected to the drain of the N-channel MOSFET, and 1 connected to the drain of the P-channel MOSFET. Here, let's start considering values. Okay. Typically, if you go to simulators, you'll find that these capacitance are not identically the same, but they are of very close values. The main factor affecting the capacitance is not its position with respect to the transistor. I mean, It's not if it's between the gate and the drain, or it's between the gate and the source, and so on. The main factor affecting the capacitance is what we can call the W, or the channel width. If you return to the basic understanding of the capacitance from a CMOS technology or from a wafer cross-sectional technology or point of view, you can understand that capacitance are mainly due to the vertical process in a MOSFET, not a horizontal one. That's why the factor L, which is a channel length, is not a or is not a contributing element for C. However, capacitance are proportional with W. Maybe those who study in details digital IDC design can understand this well. That's why when we consider capacitance, we can say that capacitance are proportional to what we call this W over L famous value. Of course, all of you have considered this W over L value when we consider different analog or digital design aspects. Why I'm considering this point? This is simply because when the capacitance, when W over L change, capacitance will change. And as you all of you have already studied, I think, the concept of the PV sizing, which is related to the variation between the electron and hole mobility. So whenever you are considering the sizing between the P MOSFET and the N MOSFET, you know that this sizing is roughly in the range of 2 to 1, which means that the W over L here is double the W over L here. So if we consider that in a normalized way, all capacitance are equal, then if I evaluate that the drain capacitance for this N-channel MOSFET is C, accordingly, the drain capacitance for this B-channel MOSFET will be 2C. Similarly, if the capacitance of the gate N-channel MOSFET is C, the capacitance of the gate B-channel MOSFET will be 2C. On this direction, we can reconsider our transistor. This is the ground. And this is the VDD. And again, here the input, of course, of this is the output. So by the end of the day, we can consider it as something like that. Here is we have a capacitance of a 3C, and here we have a capacitance of a 3C. So this is the input capacitance of the inverter, the NOT gate, and this is the output capacitance of the inverter. And using this method, you can easily express the capacitance for different logic gate designs. So let's have another example to make sure that we pick up the idea correctly. Another example. Let's have another example, which is a NAND gate. If you remember from the digital electronics classes, NAND gates are in this way. Sorry. So this is a schematic for a NAND gate, as you can see. So this is the A input, and accordingly, this is A, and this is B, and this is B, and this is out. Okay, so if you remember from your digital electronic classes, you know that the sizing here is 2, 2, 2, 2. So they are all the same as a W over L ratio. Let's now start to apply the same approach to make a capacitance model. So general okay. So let's start putting capacitance. Here, the source are connected to VDD, so we are not going to concern about the source, but with the drain, we have a capacitance here and another capacitance here. So this is 2C and this is 2C. And for the gate, we have a capacitance 2C here, and we have a capacitance 2C here. So now we finalize the gate and the drain for the first end side and the gate and the drain for the second end one. Okay. Let's go to this one on the bottom. This is easy because the source is grounded. Its gate is 2C here, and its drain is 2C. And for this one in the upper end one, so we have here the sources not grounded. So we have 2C here. We have 2C here. And we have 2C here. That's right. So in order to have an overall look, let's see. For the A inputs, which is the A input? This one and this one. So for the A inputs, we have 4C capacitors, 2C here and 2C here. For the P input, we have 2C here and 2C here. 4C again. What about the output? For the output, we have 2C, 2C, and another 2C. So we have 6C in the output. So this is the model of the capacitance for an AND gate. And don't forget that we still have internal point here with a 4C capacitance with this linking point. So as you can see here, we can start to describe the capacitance, input and output capacitance model for any logic gate using this approach so that you can estimate the input capacitance of the terminal and the output capacitance as well on the output terminal. And also we can start make a stick diagram as well as a layout for any other circuit, any other type of logic gate using the same approach. So this is what we need for this lecture. Thank you very much, my dear students, for your concentration, and see you in the next lecture, inshallah.